Go.
Hello. Today, I am delighted to present to you an exploration of weather data through the lenses of data visualization and exploratory data analysis using OpenWeatherMap. Weather plays a vital role in our daily lives, and understanding its patterns and trends can provide valuable insights for various industries, research, and decision making processes. Our project, Data Visualization and Exploratory Data Analysis of OpenWeatherMap, aims to gain valuable insights into weather patterns and trends by harnessing OpenWeatherMap's rich weather data. By utilizing data visualization techniques and explanatory data analysis, we can effectively understand and interpret the data. The team members are Sahil, Shruti, Asmit, and Athar. This is our task list. Our focus will be twofold. First, we will discover the immense potential of data visualization techniques in bringing weather data to life. We will explore a range of visualization methods that allow us to uncover meaningful patterns, correlations, and trends in the weather data provided by OpenWeatherMap. By visualizing the data effectively, we can grasp complex weather phenomena at a glance and communicate insights with clarity. This is our motivation and the references used. These are our requirements along with Python packages, libraries, and the API key. Now let's begin with the explanation of our code. The first step is to import the necessary libraries that we'll be using throughout our analysis. These libraries include requests, JSON, pandas, NumPy, datetime, time, seaborn, and matplotlib. These libraries provide us with tools and functions to handle data, visualize it, and build machine learning models. In the second code, we have defined some variables and assigned them specific values. First is the API key. This variable stores an API key that is used to authenticate and access weather data from the OpenWeatherMap API. It is a unique identifier associated with the user's account. Lat and lon. These variables represents the latitude and longitude coordinates of a specific location. In this case, it is set to the coordinates of Chicago, Illinois, with the latitude of 41.87 and longitude of minus 87.62. Next is date. This variable stores a specific date represented by a date time object. In the code, it is set to December 1st, 2022. This date is used to retrieve weather data for that specific day. CNT, this variable represents the count of weather data records to retrieve. In this case, it is set to 1, indicating that we want to retrieve data for a single hour. The purpose of this code snippet is to set up the necessary parameters to retrieve weather data for a specific location, here Chicago, and the date December 1st, 2022, using the OpenWeatherMap API. The API key, latitude, longitude, date, and count are essential parameters required to make a successful API request and fetch the corresponding weather data. The next code attempts to empty a data frame by selecting 0 rows, but it also handles the case where there is no data frame or it is already empty. The purpose of this code is to ensure that the data frame is empty before proceeding with further operations or data updates. In the next code, this function takes a value temperature value in Kelvin as input, converts it to Fahrenheit using the appropriate formula, and returns the converted value. It provides a convenient way to convert temperature values between different units within this code. In the next code, this line creates a new data frame using pd.dataframe function from the pandas library. The data parameter is set to the dictionary comprehension created in the previous step. Each key value pair in the dictionary represents a column name and an empty list. The resulting data frame is assigned to the variable df, which is now an empty data frame with the specified column names. In the next provided code, we have a loop that fetches historical weather data for a specific location from the OpenWeatherMap API and stores it in a data frame by using error handling. Date plus time plus equals date time. This line shows that there will be an increment in the date by 1 day. This is done to move to the next day for fetching the weather data. And this line start equals time dot mk time converts the date to a Unix timestamp in seconds. This timestamp will be used as a starting point for fetching the weather data. So first we constructed the URL for the API request by combining the base URL, latitude, longitude, start time, count of data points, and API key. Then we updated start variable with current data's Unix timestamp. We then sent a GET request to the specified URL and stored the response as response test. Then parsed the response text as JSON and assigned it to data new. Further, we extracted the first item from the list key of data new and assigned it to data. Then converted start Unix timestamp to a formatted date string and stored it in date string. We created a dictionary row with weather data attributes. Handling any key error exceptions using get method, we retrieved the values, setting missing values as none. Then we created a temporary data frame row df from the row dictionary. In the next step, we concatenated row df with the main data frame df using pd.concat. Then updated date by incrementing it by 1 day. Next, updated start variable with the Unix timestamp for the updated date. And finally, updated URL with the new start time for the next API request. In the next code, here we use df to print the output. And this is our output table. The data cleaning was done using the following steps. First is modifying the date column. We converted the date column in the data frame df to a datetime format using pd.toDateTime. Then extracted only the date portion, year, month, day from the datetime values using dt.dateAccessor. We assigned the modified date values back to the date column in the data frame. Second, replacing none with nan for efficient computation. The string none is commonly used as a placeholder to indicate missing or undefined values. By replacing none with nan, we can effectively represent missing data in a standardized way. Third, checking data frames for null values. df.isNA.ne allowed us to identify which columns in the data frame contain missing values. If a column had at least one missing value, it would return true for that column. Fourth, df printed the refined data. This is the output table. Then fifth was saving data for future use. This code was used to save the data frame df as CSV, that is comma separated values file, named data.csv. And then reading the data, df is equals to pd.read.csv, that is data.csv. This line reads the data from the CSV file, that's data.csv, and creates a data frame df containing that data, allowing us to work with the data in a structured manner using pandas. Next is data analysis. So this code snippet provided is used to create a line plot to visualize the relationship between time, date, and temperature. So sns.set is used to set the default style of the plot to the Seaborn style. sns.lineplot creates a line plot using Seaborn line plot function. It specifies that the x-axis values should be taken from the date column of the data frame df and the y-axis should be taken from the temp column. plt.xtext rotation equals 75 ha equals right sets the rotation and alignment of the x-axis tick labels. The rotation 75 parameter rotates the labels by 75 degrees and ha equals right aligns them to the right, ensuring better readability if the labels are long. plt.title sets the title of the plot as temperature versus time. plt.xlabel sets the label for the x-axis as date. plt.ylabel sets the label for the y-axis as temperature f, indicating that the temperature is measured in Fahrenheit. plt.show displays the plot. So overall, the code generates a line plot showing the relationship between time, date, and temperature with properly labeled axis and a title for better understanding and presentation. Histogram. Overall, the code generates a histogram in the form of a kernel density estimate plot showing the distribution of temperature values. The plot helps visualize the concentration of temperature values and provides an understanding of the distribution. Next to histogram is the density versus Fahrenheit. It creates a KDE plot using Seaborn's KDE plot function. It specifies that the data is taken from data frame df and includes the column fields like temp min, temp max, and temp. This creates separate KDE plots for each temperature variable, showcasing their individual distributions. It also sets the title of plot as kernel density estimation graphs. The plot helps understand the shape and density of each variable's distribution and provide insights into their respective temperature ranges. Temperature versus speed. This creates a KDE plot using Seaborn's displot function. It specifies that the data is taken from the data frame DF and uses temp column as the x-axis variable and the wind speed column as the y-axis variable. The kind equals KDE parameter indicates that a 2D KDE plot should be generated. The resulting plot provides an estimate of the density of points in the temperature, wind speed space, representing the joint distribution of these two variables. It allows you to observe any patterns or correlations between temperature and wind speed, helping you understand their relationship. Humidity distribution. It creates a Voilin plot using Seaborn's Voilin plot function. It specifies that the data is taken from humidity column of the data frame DF. The Voilin plot displays the distribution of humidity values, showing the quartiles, median, and overall distribution shape. The resulting plot provides an overview of the humidity distribution, indicating the central tendency and the spread of the data. The width of the Voilin shape represents the density of humidity values at different levels, with a wider section indicating a higher density of data points. Then comes the wind speed distribution. It creates a Voilin plot using Seaborn's Voilin plot function. It specifies that the data is taken from wind speed column of the data frame. The Voilin plot displays the distribution of the wind speeds, showing the quartiles, median, and overall distribution shape. Then correlation heat map. It creates a heat map using Seaborn's heat map function. It computes the correlation coefficients between the selected weather variables like temperature, feels like pressure, humidity, temp min, temp max, wind speed, gust from the data frame DF and displays them as color-coded heat map. The colors in the heat map indicate the strength and direction of the correlations. Darker color represent stronger positive or negative correlations, while lighter color indicate weaker or no correlations. The heat map helps identify relationships between variables such as whether temperature and humidity have a positive or negative correlation. Regression analysis. It replaces missing values in the data frame DF with the mean values of the respective columns. This ensures that there are no missing values in the data set. It selects a subset of columns from the data frame DF and assigns them to the variable X. These columns represent the independent variables used for prediction. It calculates the coefficient of determination R squared for the trained model using testing data. It measures the proportion of the variance in dependent variable that can be explained by the independent variables. So before classification, we used the trained regression model regressor to predict the values of the dependent variable feels like based on the independent variables, which are temperature, pressure, humidity, wind speed, gust in the test dataset X test. By calculating and examining the MSE, you can assess how well the regression model fits the data and evaluates its predictive accuracy. For the classification, we created an instance of the SVM classifier with a linear kernel. The linear kernel is suitable for problems with a linear decision boundary. We trained the SVM classifier on a training data using the fit method, which learns the patterns in the features and their corresponding target labels, then made predictions on the testing data by calling the predict method. Then by training and evaluating SVM classifier, we assessed its ability to classify the weather description based on the given features and determine its overall accuracy in predicting the description weather conditions. The last code calculates a confusion matrix using the confusion matrix function. The confusion matrix provides a summary of the classification results by comparing the predictive labels YSVM predict with the actual labels YSVM test from the testing set. It shows the number of true positive, true negative, false positive, and false negative predictions. Then we created a heat map visualization of the confusion matrix using heat map function from the Seaborn SNS. The classification report provides metrics such as precision, recall, F1, and support for each class in the target variable YSVM test based on the predictions. By generating and visualizing the confusion matrix and printing the classification report, we can assess the performance of the linear SVM classifier in the terms of its accuracy, precision, recall, F1 score, and other metrics for each class. These are the instructions to run the code. And these are the future modifications of our project, which include extreme weather events analysis, performing sentiment analysis, and combining with launch operations data. Thank you.